Look here. As we have discussed earlier, box of ABC into box of LMN, where A bar is equal to A1I plus A2Z A3K, B bar is equal to B1I plus B2Z plus B3K, C bar is equal to C1I plus C2Z plus C3K. Meanwhile, L bar is equal to L1I plus L2Z plus L3K, M bar is equal to M1I plus M2Z plus M3K, N bar is equal to N1I plus N2Z plus N3K. We have proved as box of A bar, B bar, C bar is equal into that is L bar, M bar, N bar. It's an ordinary product, or else if you want you can remove this. This is nothing but det A bar dot L bar, A bar dot M bar, A bar dot N bar, B bar dot L bar, B bar dot M bar, B bar dot N bar, C bar dot L bar, C bar dot M bar, C bar dot N bar. Later, we have proved box of ABC whole square is equal to, instead of box of LMN, we have taken again box of ABC. Now in place of L, box of ABC whole square is equal to, in place of L, M, N, substitute A, B, C. A dot A, A dot B, A dot C. B dot A, B dot B, B dot C. C dot A, C dot B, C dot C. Now let us discuss about box of A bar, B bar, C bar into L bar cross M bar. L bar cross M bar. Now, I can take this one as A1, A2, A3, B1, B2, B3, C1, C2, C3, L cross M, I, J, K, L1, L2, L3, M1, M2, M3, followed. Now coming to this one is first row with first row. I can write in a determinant, as I told, you can multiply row with a row, column with a column, row with a column, column with a row. There is no restriction in determinant, but there is a restriction in matrices, row with a column or a column with a row. So therefore, now first row with first row, it becomes A1I, it becomes A2Z, it becomes A3K. Next, A1L1, A2L2, A3L3. Next, A1M1, A2M2. This becomes A3M3. Meanwhile, second row with first row, I can write B1I, B2Z, B3K. Second row with second row, B1L1, B2L2, B3L3. Next, B1M1 plus B2M2, B3M3. Next, third row with first row, C1I, C2Z, C3K, C1L1, C2L2 plus C3L3. Next, C1M1 plus C2M2 plus C3M3. If L bar is equal to L1I plus L2Z plus L3K, M bar is equal to M1I plus M2Z plus M3K, meanwhile A bar is equal to B bar is equal to C bar, as you know already, A1, A2, A3, B1, B2, B3, C1, C2, C3. This is nothing but A bar, B bar, C bar. This is a dot product of A bar and L bar. A bar dot L bar, A bar dot M bar, B bar dot L bar, B bar dot M bar, C bar dot L bar, C bar dot M. So therefore, you have a much applications of these product of two determinants, especially while finding the volume of a what parallelepiped or volume of a what tetrahedron also, because the volume of a parallelepiped is equal to box of ABC. Okay, let us recall these concepts all this. Box of ABC whole square, box of ABC into box of L bar, M bar, N bar. Next box of ABC into what? L bar cross M bar, by giving what? Some vivid example as I desired in finding the what? Volume of a parallelepiped. Yes. One more example in analyzing the box of ABC. I take, let alpha bar is equal to alpha 1 comma alpha 2 comma alpha 3, beta bar is equal to beta 1 comma beta 2 comma beta 3, and gamma bar is equal to gamma 1 comma gamma 2 comma gamma 3. Means alpha bar is equal to, that is alpha 1 into I plus alpha 2 into Z, alpha 3 into K. Similarly, beta bar and gamma bar. And modulus of alpha bar is equal to something he has given 2. When modulus of alpha bar is equal to 2, meanwhile, the angle made by angle between the vector alpha bar and the plane generated by beta bar and gamma bar is pi by 6. Pi by 6, and angle between the vectors beta bar and gamma bar is what? Pi by 4. Then det of, that is alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3, whole power n is equal to dash, where n is a natural number or even natural number, right? Even natural number. Look here, you can very well observe determinant is nothing but a what? Box. Box of what? This is nothing but det of alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3 is nothing but a box of alpha bar, beta bar, gamma bar. Later we can take n. So this is proof of this one is very simple. Now let us take, this is beta bar, this is gamma bar, and angle between them is what? Pi by 4. Now if I take, this is the vector n cap, I mean this is nothing but beta bar comma gamma bar. If you want, you can take somewhere this vector alpha bar somewhere, or else here also you can take, it makes no difference. So therefore, now given alpha 1, alpha 2, alpha 3, it's a beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3 is nothing but box of alpha bar, beta bar, gamma bar. In turn, I can write this one as alpha bar dot b bar cross gamma bar. So when you have taken the dot product, why I combined these two? Because he has given the angle between beta and gamma, that is pi by 4. Means I can write beta and gamma is equal to pi by 4. Meanwhile, alpha bar comma n cap is equal to what? Pi by 6 is nothing but alpha bar comma beta bar cross gamma bar is equal to pi by 6. Now, by definition of a cross product, beta bar cross gamma bar is the vector perpendicular to the plane containing beta bar and gamma bar. Nevertheless, That is the angle between alpha bar and n cap is what? Pi by 6. In turn, n cap is the unit vector which is perpendicular to the plane containing beta bar and gamma bar. Followed? So therefore, n cap identifies or specifies the plane generated by beta and gamma. Nevertheless, it's a plane. It means that this pi by 6 is the angle between the vector alpha bar and a plane. As we are known already, the angle between the two vectors is a cos theta a bar dot b bar by modulus of a bar into modulus of b bar, provided if you are finding the angle between a bar and b bar. So here now it is a plane and a vector. So therefore, angle between a plane and a vector is a complement of the angle between the two vectors, or a complement of the angle between the two straight lines. So therefore, what I do is the angle between alpha and n cap, alpha bar and n cap is the angle between the plane and a what vector, means cos of 90 minus theta is the angle between what line and a plane, angle between line and a what plane. So therefore, now I can take this one as alpha bar modulus of alpha bar modulus of gamma bar cross, this is beta bar cross gamma bar into cos of 90 minus theta. So therefore, this is nothing but 2 into modulus of beta bar gamma bar sin theta. So therefore, since theta is equal to what? Pi by 6. So therefore, 2 into beta bar gamma bar into what? Sin pi by 6. Okay, this is nothing but 2 into 1 by 2 sin pi by 6 is 1 by 6. Therefore, beta bar cross gamma bar, this is. So therefore, this and this get cancels. Modulus of beta bar gamma bar, this is nothing but modulus of beta modulus of gamma into sin pi by 4, angle between the two vectors is sin pi by 4 into modulus of n cap. Why? Because by definition of the cross product of beta bar cross gamma bar, mod beta into mod gamma into sin theta, sin that is sin pi by 4 into n cap. Take the modulus. So therefore, now this is nothing but modulus of n cap is equal to 1. This becomes 1 by root 2 into beta into gamma, beta bar into gamma bar. This is 1 by root 2, this is 1. So therefore, this is nothing but the determinant. I want the determinant to whole power n. Whole power n is nothing but beta bar gamma bar, that is whole power n, whole divided by 2 power of, that is root 2, that is 2 power of whole power what? N. So therefore, I can write this one as modulus of beta bar modulus of gamma bar by what? Root 2 whole power n is the required answer. That is between what? Angle between beta bar and gamma bar is pi by 6, and what? That is plane generated beta bar and gamma bar is what? Pi by 4, and the plane generated by beta and gamma is pi by 6, and the angle between the vectors beta bar and gamma bar is pi by 4. Then the value of this is given to be mod beta into mod gamma by root 2 whole power n. Here, the angle between the two vectors is there, angle between a vector and a plane is also there. This is by using the what? Scalar triple product. Scalar triple product. After knowing the what? The volume of a parallelepiped, let us use the definition of scalar triple product in proving three vectors as coplanar. Means the necessary and sufficient condition for any three vectors A bar, B bar, C bar to be coplanar is box of A bar, B bar, C bar is equal to 0. So therefore, I start It's a concept. Let A bar, B bar, C bar be three non-zero, non-collinear vectors to be coplanar. Is box of A bar, B bar, C bar is equal to 0. Sometimes it can also be interpreted as the necessary and sufficient condition for the three non-zero, non-collinear vectors A bar, B bar, C bar to be coplanar is a box of A bar, B bar, C bar is equal to 0. Nevertheless, det of those vectors is equal to 0. So therefore, you can use, if A bar is equal to A1i plus A2j plus A3k, B bar is equal to B1i plus B2j plus B3k, C bar is equal to C1i plus C2j plus C3k. When box of A bar, B bar, C bar is equal to 0, then determinant containing the coefficients of ijk, scalar components, det of A1, A2, A3, first row, second row, B1, B2, B3, third row, C1, C2, C3 is equal to 0. Let us see how this says. I start. Let A bar, B bar, C bar be three non-zero and non-parallel vectors. Now, let A bar, B bar, C bar be the vectors lying in a same plane. Which implies A bar, B bar, C bar are coplanar. I have considered, or else the necessary condition, how do we prove is, assume that A bar, B bar, C bar as coplanar. We have to show that box of A bar, B bar, C bar is equal to 0. So therefore, I have taken, by definition of cross or vector product of A bar and B bar, the vector A bar cross B bar is perpendicular to the plane containing B, that is A bar and B bar. Since C bar is also lying in the same plane. What's the definition of coplanarity? When three vectors are lying in a same plane or a parallel planes, we call it as what? Coplanarity. This is the plane. It may contain three vectors, it may contain 100 vectors. If A cross B is perpendicular to A bar and B bar which are lying in that plane, then that vector A cross B is also perpendicular to C bar and also perpendicular to any number of vectors when they are lying in a same plane. Followed? So therefore, now is also lying in the same, which implies A cross B is also perpendicular to C bar, which implies by definition of dot product, when any two vectors are said to be either perpendicular or orthogonal, we have proved A bar dot B bar is equal to 0. A bar dot B bar is equal to 0. So therefore, which implies A bar cross B bar is a one vector, C bar is another vector, is perpendicular to 0. Nevertheless, this is nothing but scalar triple product. A cross B dot C bar, which implies I can write as box of A bar, B bar, C bar is equal to 0. You observe the what? The way in which the analogous says, the way in which we are working is, we have considered A bar, B bar, C bar as a coplanar. We could prove box of A bar, B bar, C bar is equal to what? 0. It means that the necessary condition for any three vectors to be coplanar is what? Box of A bar, B bar, C bar is equal to 0. Now sufficient condition. What is sufficient condition? Whenever, wherever, if you come across box of A bar, B bar, C bar is equal to 0, then A bar, B bar, C bar are coplanar. They are lying in the same plane. Let us see. What I am going to do is the case 1. This is, you can take as a case 1. I am going for what? Case 2. Let A bar, B bar, C bar be three non-zero, non-parallel vectors. Now consider, let box of A bar, B bar, C bar is equal to 0. Box of A bar, B bar, C bar is equal to 0. When box of A bar, B bar, C bar is equal to 0, box is in turn is a scalar triple product. I can also write A bar dot, that is A bar cross B bar dot C bar is equal to 0. Sir, can we write A dot of B cross A as you please? Shall we write A C cross A dot B bar as you please? But it is customary that here we have taken A cross B, better to go for the uniformity. Because of that reason, I could consider A cross B dot C bar. So therefore, A bar cross B bar dot C bar is equal to 0. So therefore, whenever, wherever the dot product of any two vectors is equal to 0, it is quite obvious they are perpendicular to each other or orthogonal. So therefore, I can write A cross B, A bar cross B bar is perpendicular to C bar. Since A bar comma B bar are lying in the plane of C bar, which implies A bar comma B bar comma C bar are coplanar. So therefore, what we have proved? We have considered box of A, B, C is equal to 0. We have shown A bar, B bar, C bar as coplanar. Remember, the necessary and sufficient condition, or another way is, let A bar, B bar, C bar be three non-zero, non-collinear vectors to be coplanar is box of A bar, B bar, C bar is equal to 0. Now, so he has given A bar, B bar, C bar lying in a same plane, which implies we have considered A bar, B bar, C bar as coplanar. By definition of cross or vector product of A bar and B bar, the vector A cross B is perpendicular to the plane containing A bar and B bar, which implies when A cross B is perpendicular to the plane containing A bar and B bar, since C is also lying in the plane of what? A bar and B bar, same plane, which implies A cross B is also perpendicular to what? C bar. Whenever the dot product of any two vectors is equal to 0, so therefore then they are perpendicular, box of ABC is equal to 0. We have assumed coplanar, we have shown box of ABC is equal to 0. Consider box of ABC is equal to 0. Then A cross B dot C bar by definition of scalar triple product. So when A cross B is perpendicular to C bar, since A bar comma B bar are lying in the what? Plane of C bar comma B bar. C bar. So therefore, A cross B is also perpendicular to what? A bar comma B bar. If you want, you can take it. This is A bar comma B bar lying in the plane of C bar. It understands, it explains when A cross B is perpendicular to C bar, it is quite obvious A bar cross B bar is also perpendicular to A bar and B bar. That's the meaning of this. So therefore, now which implies A bar, B bar, C bar are what? Coplanar. Hence, hereafter, the necessary and sufficient condition for any three vectors to be coplanar wise, box of A bar, B bar, C bar is equal to 0. Right? Yes, let us recall the definition of the coplanarity according to scalar triple product. I take one example as the desired. Let A bar is equal to I plus 2j minus AK. B bar is equal to 2i minus 2j, C bar is equal to 3i minus j plus 4k. B3 coplanar vectors, then A is equal to dash. Now what I do is just you find out what he has given. The given is, look here, given A bar, B bar, C bar are coplanar, which implies box of A bar, B bar, C bar is equal to 0, which implies determinant 1, 2 minus A is equal to 0. 2 minus 2, 0. 3 minus 1, 4 is equal to what? 0. Come on, expand it. Look here. And also, you can ask one question, sir. Can you write? You told two theorems. One theorem is when the given vectors are expressed as a base vector as Ijk, you can write box of ABC is equal to det into box of Ijk. But box of Ijk is equal to, we have proved 1. So now, if the vectors are given in terms of other base vectors, say for example, P bar, Q bar, R bar, P bar, Q bar, R bar, P bar, Q bar, R bar, you write down the coefficients of box of ABC is equal to, the determinant contains the coefficients of B bar, Q bar, R bar into box of ABC you are supposed to write. But here the situation is in terms of Ijk, no need. So now you expand 1 into, that is minus 8, AD minus BC, leave this row, this column, minus 8, minus 0, minus 1 into, minus 2 into 8 minus 0, minus A into, I can go for minus 2 plus 6 is equal to 0. So therefore, I can write minus 8 minus 16, yes, come on, minus 4a is equal to 0. So therefore, simplify, this becomes 4a is equal to, yes, 4a is equal to minus 24. Now you simplify, this becomes, it is minus 6 is the answer. This is how you can find out the unknowns under the concept of what? Coplanarity. Under the concept of coplanarity, right? Now look here. Let us recall the concept of box of A bar, B bar, C bar is equal to 0 when A bar, B bar, C bar are coplanar, by giving another good example with supporting that concept. What is that? A bar is given, B bar is given, C bar is given. What is A bar? 1 minus 2, 3. I minus 2j plus 3k. B bar is equal to 2i plus 3j minus k. C bar is equal to lambda I plus j plus 2 lambda minus 1 into k. So, if C bar is parallel to plane of A bar comma B bar, C bar is parallel to the plane of A bar comma B bar means they are what? Coplanar. What's the definition of coplanarity? When the vectors are lying in a same plane or parallel planes, we define them as aptly coplanar vectors. So therefore, A bar, C bar is parallel to the plane of A bar comma B bar means they are coplanar. I can write the solution of this one is, now given, what is given? C bar is a parallel to the plane of A bar comma B bar, which implies A bar comma B bar comma C bar are coplanar, which implies box of A bar, B bar, C bar is equal to 0. Since the given vectors are in terms of what? Ijk, no need to write that into box of Ijk. So therefore, now you write on the coefficients of Ijk, 1, minus 2, it's a 3, this is 2, it's a 3, minus 1, lambda, 1, it's a 2 lambda minus 1. Okay, so now let us expand this one is, what I can write is, by expanding, right? Yes, now 1 into 3 into this, 6 lambda minus 3. Now minus of minus plus 1. This into this into this, AD minus BC. Minus of minus plus 2 here. Now 2 into this, 1 into this. Now I can write 4 lambda minus 2. Minus of minus plus lambda plus 3 into, what is that? 2 minus 3 lambda. 2 minus 3 lambda is equal to 0. Now you simplify, which implies 6 lambda minus 2. This becomes what? 5 lambda. 10 minus 10 lambda minus 4. 4 lambda plus lambda, 5 lambda minus 2. Now multiply with 2. This becomes 6 minus 9 lambda is equal to 0. So therefore, I can write 10 minus 9 lambda, that is a lambda. Lambda plus 6 lambda, 7 lambda. Next, minus 6. Now minus 2, minus 4, 6. This get cancels, is equal to 0. Therefore, we got it. Lambda is equal to 0 under the constraints of what? C bar is parallel to the plane of A bar comma B bar. Nevertheless, when A bar, B bar, C bar are coplanar, we have found out the lambda is equal to what? 0 by applying box of ABC is equal to 0. That has a desired value. Yes. Students, let us discuss about another three-dimensional figure. It's a tetrahedron. As we have discussed about parallelepiped. Parallelepiped is nothing but take a rectangle, apply some force or a weight on a rectangular box. Every faces of a rectangular box will turn into a parallelogram. That we call it as a parallelepiped. Now I go to what? Tetrahedron. What is how many faces? What are its structural conditions? If I take A, if I take B, if I take C and D. So therefore, tetrahedron and regular tetrahedron. In tetrahedron, let us see, it has how many edges, how many faces. So, look here. A, B, C and D are the four vertices. And there are how many edges? AB bar, AC bar, AD bar, BC bar, CD bar, BD bar. 1, 2, 3, 4, 5, 6. It has 6 edges. Then it has how many faces? 4 faces. And each face will be the triangle. How many faces? Now look here. Triangle ABC 1. This is 1. This is first face. This is second face. This is third face. What you can see, the triangle ABD is another face. This pictorial representation comes under the 3D approach. It's difficult to convince. So therefore, it has how many faces? 4 faces. One is ABC, triangle ABC, triangle BCD, triangle ADC, triangle what? ABD. So therefore, tetrahedron has 6 edges and 4 faces. Each face will be the what? Triangle. In a tetrahedron, ABCD, it has 4 faces, and each face will be the triangle. And the second one, it has 6 edges, that is, or else they are AB bar, next AD bar, next BD bar, next AC bar, next BC bar, CD bar. So therefore, when it has 6 edges, 4 faces, and each face is a triangle, let us apply the concept of scalar triple product, box product, in finding the volume of a tetrahedron. It is, as we have proved, in geometrical interpretation of scalar triple product as a volume of a parallelepiped, in the same fashion, we have to prove that the volume of a tetrahedron as 1 by 6 into box of A bar, B bar, C bar, where A bar, B bar, C bar represents the edges. A bar, B bar, C bar represents the edges. The volume of the tetrahedron ABCD is 1 by 6 into box of AB bar, AC bar, AD bar. Right. Let us take the tetrahedron A, B, D, this is C. Now, this is AB bar, AD bar, AC bar. Define a cross product between AB bar and AD bar or AC bar. Now I can write, this is nothing but n cap. I can write AB bar cross AC bar. Why? This is a triangle. This is one plane, one face. Now, the area of this triangle ABC can be written as, that is of into AB bar cross AC bar. Before that, by definition of what? Vector array cross product, AB bar cross AC bar is the vector which is perpendicular to the plane containing plane of ABC or containing AB bar and AC bar. We call it as plane ABC. Then from this AD, you draw a perpendicular, you call it as what? H. This is nothing but what? DH. DH is nothing but the perpendicular from the vertex to the D, from the vertex D to the plane ABC. So therefore, how to find out this length DH? I start now. The volume in a tetrahedron ABCD, the volume of tetrahedron ABCD is equal to 1 by 3 into area of triangle ABC into DH. I call it as DH. What is DH? But before that, 1 by 3 into area of triangle ABC. We know that area of a triangle ABC is nothing but of into modulus of AB bar cross AC bar into DH. Yes, we got it as 1 by 6 into modulus of AB bar cross AC bar into DH. Now, when AB bar, AC bar and N cap, or else when AB bar, AC bar, AD bar are in right-handed system, then the projection of AD bar on N cap is positive. Means the terminal points are on the same side. Okay? If they are in left-handed system, means when the terminal points of N cap and AD are in what? Opposite side, projection is negative. Means the angle between them is what? Obtuse. So therefore, what I do is, instead of taking what common, yes, negative and positive, I go directly. Means when they are in right-handed system, I can write plus. If they are in what? Left-handed system, I can write minus. You can also make use of one of the tool in finding when A bar, B bar, C bar to be in what? Right-handed system or left-hand system. By using this, you can find out. We also find out the volume of the parallelepiped is equal to plus or minus box of A bar, B bar, C bar. Plus indicates right-handed system, minus indicates what? Left-handed system. Meanwhile, volume cannot be negative. We take it as modulus. It cannot be minus. Here also, to decide AB bar, AC bar, AD bar, whether they are in what? Left-handed system or right-hand system, we go according to the volume of a tetrahedron. So therefore, now but volume of a tetrahedron cannot be negative. It is always what? Positive. So therefore, now what I do is, DH is equal to, I can write 1 by 6 into box of AB bar, AC bar into the projection of DH, that is AD bar on AB bar cross AC bar. I can also write N cap. But on N cap, AB bar cross AC bar is collinear. So therefore, now projection of AD bar on AB bar cross AC bar. If they are in right-handed system, positive. If they are in left-handed system, negative. Okay. So therefore, I can write half into 1 by 6 into modulus of AB bar cross AC bar by using the definition of projection of A bar on B bar as we have come across in the dot product is projection of A bar on B bar is A dot B by modulus of B, right? On B, modulus of B. Already we have proved. So therefore, in the same fashion, I can also write AD bar dot AB bar cross AC bar by modulus of AB bar cross AC bar. Now this and this get cancels. Nevertheless, I can write volume of a tetrahedron is a box of AB bar, AC bar, AD bar. This is the volume. Why? It's a scalar triple product. Hereafter, the volume of a tetrahedron ABCD can be written as 1 by 6 into box of AB bar, AC bar, AD bar. Yes, we have taken the sides. In place of what? AB bar, AC bar, AD bar, if I consider them as A bar, B bar, C bar, then what happens? Now if I take them as, if AB bar is equal to A bar, AC bar is equal to B bar, AD bar is equal to C bar, then, okay, then the volume of tetrahedron is V is equal to 1 by 6 into plus or minus box of A bar, B bar, C bar. Plus indicates they are in what? Right-handed system. Minus indicates they are in what? Left-handed system. Yes, you are talking about the edges. Sometimes he gives the position vectors. Capital A is equal to OA bar is equal to A1I plus A2J plus A3K. OB bar is equal to B1I plus B2J plus B3K. OC bar is equal to C1I plus C2J plus C3K. OD bar is equal to D1I plus D2J plus D3K. Then find out the volume of a tetrahedron. The volume of a tetrahedron. You can write directly, yes, come on, AD bar. What you can write? Note, if OA bar is equal to A1, A2, A3, OB bar is equal to B1, B2, B3, means A1I plus A2J plus A3K. B bar is equal to B1I plus B2J plus B3K. OC bar is equal to, yes, C1I, C2J, C3K. And OD bar is equal to D1, D2, D3 are vertices of a tetrahedron ABCD. Then its volume V is equal to, we know that 1 by 6 into box of AB bar, AC bar, AD bar. Okay, now this is nothing but 1 by 6 into OB minus OA, OC minus OA, OD minus OA. Sir, why you are taken co-initial vectors? I told many times, oftenly. Whenever you are given with the 4 points, you have to prove them as a coplanar. Means they are lying in the same plane. Tetrahedron is nothing but a plane. So therefore, whenever you are proving them as a plane or a coplanar, you are supposed to construct them as a co-initial vectors. Then why you take only AB bar, AC bar, AD bar? Yes. I never said you have to start with only A. We can go for what? AB bar, AC bar, AD bar. BA bar, BC bar, BD bar. CA bar, CB bar, CD bar. Or DA bar, DB bar, DC bar, as you please. Okay, you can go with anyone as an initial point. No restriction in that. So therefore, now this represents a first row, this represents a second row, this represents what, third row. I can write volume V is equal to 1 by 6 into det. Why det, sir? Det is nothing but scalar triple product, box product. So therefore, now I can write OB minus OA, that is B1I minus A1I is nothing but B1 minus A1 into I plus B2 minus A2 into Z, B2, next plus B3 minus A3 into K. These are the coefficients of what? I, J, K. Next, what is the command? OC minus OA, C1I minus A1I, therefore C1 minus A1 into I. Next, C2 minus A2 into J. Next, C3 minus A3 into K. Next, now OD minus OA, therefore D1 minus A1, D2 minus A2, D3 minus A3. This is nothing but the volume of a tetrahedron when their position vectors of the vertices are given. If you prove them as is equal to 0, certainly it satisfies given 4 points are coplanar. 4 points are coplanar. Thank you.